Good morning, everyone, and thank you for joining us today for today's bonus presentation on the Mountain Plains Consortium Research Project MPC-540, updating and implementing the Grade Severity Rating System, or GSRS, for Wyoming mountain passes. This presentation is being brought to you by the Transportation Learning Network, or TLN. TLN is a program of the Upper Great Plains Transportation Institute at North Dakota State University and is a partnership with the 4 state DOTs of North Dakota, South Dakota, Montana, and Wyoming, and the Mountain Plains Consortium, which includes 8 universities in Colorado, North Dakota, South Dakota, Utah, and Wyoming. Again, our presentation today is the research findings on MPC 540, updating and implementing the Grade Severity Rating System for Wyoming mountain passes. Our presenter today is Milhan Moomin. He has his PhD. He got his bachelor's degree from the Kwame, I'm going to mess this up, Nkrumah University of Science and Technology in Ghana, then worked for Ghana Highway Authority as a contracts engineer. He subsequently received a master's degree from Purdue University in 2016, where he researched on bridge infrastructure management. He obtained a PhD in civil engineering in August of 2019 with a research focused on truck safety from the University of Wyoming. Dr. Moomin is currently working as a postdoctoral research associate with the Wyoming Technology Transfer Center at the University of Wyoming. Milhan, if you want to go ahead and begin your presentation, I'll hand it over to you.
Thank you, Chris. Hello, everyone. Like Chris said, my name is Milhan Moomin, and I'm going to be talking to you about updating and implementing the Grade Severity Rating System for Wyoming mountain passes. The principal investigator who worked with me on this research is Dr. Khalid Sabati. He's the director for the Wyoming Technology Transfer Center here in the University of Wyoming. So let's move on then. Okay, so let's begin the presentation then. So this will be the outline of my presentation. I'll introduce research to you, talk about the research tasks, what we did in updating the GSRS. I'll then discuss formulation of weight-specific speed science and take you through an example. I'll also discuss recommendations we made from the study and future research. Mountainous highways present very challenging environments for trucks and truck drivers. This is because the trucks carry very heavy loads, and on mountain highways you have steep downgrades, and these downgrades are often long, and this combination makes them very hazardous. A lot of energy is generated, potential energy is generated on these steep downgrades. And to dissipate the energy which comes about as the truck is moving, brakes have to slow the trucks down using friction. So they convert kinetic energy, which is converted to heat energy and dissipated into the environment. However, this continuous braking results in very high temperatures for the brake systems, and this has the potential to lead to brake failure due to the brakes heating to such an extent that braking capacity is totally lost. And crashes resulting from brake failure on steep downgrades are known as runaway crashes, and they are often devastating. Sorry, I missed a few slides there. So this is an example of a runaway crash. This happened in China. Let me go back a bit. So here you can see that the truck has lost complete control. The driver is no longer in control of the truck, and this crash led to the death of 5 people. And our research is aimed at preventing these sort of runaway crashes. So in the US here, there have been recent runaway crashes. In April, on April 25th this year, there was a runaway crash in Denver, close to Lakewood. It was in Lakewood. This crash resulted in the death of 4 people. A 23-year-old driver who was driving a semi-trailer lost his brakes, and the truck gained a speed of 85 miles an hour in a 45 miles an hour speed zone. There was a slowdown of vehicles, unfortunately, and this truck crashed into the traffic, and there was a 28 vehicle pileup leading to the death of 4 people. In Wyoming on October 1st this year, there was another crash. A truck coming from Idaho loaded with potatoes and onions lost his brakes. Unfortunately, the driver couldn't use the ramp, the gravel ramp. Neither could he use the cable catch net system because it was under repairs. And so the driver crashed into a wide-dot sand shed. The cab of the truck detached. Fortunately, the driver sustained minor injuries. There was no fatalities in this incident. You can also see another crash of a tanker rolled over on US 14. That was some years ago. Also this year, you had 2 semi-trailer crashes in Woods Landing in Wyoming here, and this happened within a space of a month, and the second semi-trailer crash led to the death of a driver. So what I'm trying to show here is that runaway truck crashes are often devastating. They have very bad impact on lives and property. So trucks have a peculiar problem when they descend steep downgrades. Like I mentioned before, high temperatures increase the risk of brake failure. These temperatures cause drums to expand. This is for drum brakes. So you have the drums expanding, becoming distorted in shape. You have the outer part of the drum expanding so much that the drum takes on the shape of a bell. This is known as bell mouthing. And as this distortion continues, the available distance for the brake lining and brake shoe to travel increases. This means that there isn't a great contact between the brakes and the drum surface, meaning there's a loss of braking efficiency as this continues. This phenomenon is what is known as brake fade. And as brake fade continues, the truck gains speed, which will become uncontrollable. And a total loss of control may occur, just like what you saw in the video. And you have those sort of bad runaway crashes. So to counter the incidence of truck runaways on downgrades, grade rating systems have been developed since the 1950s. What these systems are meant to do is to inform drivers of upcoming severe grades, also to enable the drivers modify their behavior, such as selecting low gears and selecting appropriate speeds to descend these steep downgrades. Previous rating systems have included the Bureau of Public Rules rating system developed in the 1950s, the Higgs grade rating system developed in 1963, and the Lills grade rating system developed in 1975. However, some of these previous rating systems were considered to be arbitrary, and variations within grade categories created confusion among the drivers. Important variables such as initial brake temperatures, ambient brake temperatures, heating and cooling characteristics of the brakes were not considered in some of these systems. And for a lot of the previous rating systems, drivers were still required to use their experience to safely travel over steep downgrades. So in the late 1970s, the Federal Highway Administration initiated a research project to develop a grade severity rating system. This rating system used a related brake temperature to the speed of a representative track, such that when a truck chooses a particular speed and descends at a steep downgrade, at any point within the downgrade, it will still have enough braking capacity to safely descend that downgrade. And this was accomplished through the use of weight-specific speed signs. And you can see an example of a weight-specific speed sign on this slide. You have the weight categories and the maximum speed for each weight category. Importantly, this GSRS model considered track weight, it considered the physical characteristics of the downgrade and the heating and cooling characteristics of the track brake system. It also considered environmental conditions which would affect the brake system temperature. However, in the intervening decades since the GSRS was developed, efforts to conserve fuel and reduce gas emissions has led to radical changes in track designs. So right now the tracks are more streamlined. They have reduced frontal areas. They also have lower rolling resistance due to the change from bias ply to radial ties. They also have lower engine friction. What this means is that retardant forces which were available to trucks in the 1970s and 80s have now been reduced substantially to a point that the brakes have to do a lot more of the work. On the other side, truck brakes have been enhanced due to the federal reduced stopping distance mandate. This mandate required trucks to reduce their stopping distances by up to 30% for certain for new models of trucks by the year 2013. Also, engine horsepower and braking forces from truck engines have increased over the decades. They are now between 400 to 550 horsepower. At the time the grade severity rating system was developed in the 1980s, the retardant horsepower was about 170. Right now you have retardant horsepower which could be as high as the thrust horsepower of these modern trucks. So the objectives of the study. It is essential to know that this research was a comprehensive study of mountain pass safety in Wyoming. However, for this research, I'm going to be focused mainly on updating the GSRS. So our first objective was to update the GSRS to reflect current track population characteristics and make recommendations for implementation. The second objective was to evaluate mountain passes and their warning system with regards to downgrade track crashes. For this presentation, I'll give highlights about our findings for the second objectives, but I'm not going to go so deep into it. So to the research task. First, these are the research tasks. We had to select a representative track. We had to develop testing protocol for field testing, instrumenting test track, undertaking the field test, and updating the GSRS to determine maximum descent speeds and make recommendations for implementation. So to the first task, selecting a representative track. We selected a single trailer 5-axle track. This choice was made because this track configuration represents about 60% of tracks on US highways currently. Our test track was a Kenworth T680 series, the 2016 model. It had a 13-speed transmission. The trailer was a Hyundai trailer van with a gross vehicle weight rating of 65,000 pounds. The test engine was a Cummins ISX-15 engine 2013 model with a horsepower of 550. The operating speed range was 1,200 to 2,000 RPM, and it was fitted with the compression engine brake, also known as the Jake engine brake. The truck was fitted with the Bendix air disc front brakes. This was for the steer axle. All the other wheels had the Castellite S-cam drum brakes for both the tractor and the trailer. So to the testing protocol. We developed a testing protocol to guide us during our testing procedure. This included procedures for site selection, test vehicle preparation, and the actual test procedure. I'll talk about the test procedures in a moment. So to instrument the test track, we installed infrared sensors on all 10 brakes. We also installed signal conditioning and power distribution boxes on the tractor and the trailer. What these were meant to do was to collect information from the infrared sensors and also deliver power to these sensors. There was another conditioning box in the cab, and power supply was provided by the truck. There was also communication with the truck engine to get some important variables. There was a brake pressure transducer to measure the application pressure during the test. So all the data was collected to the controller box in the cab, and this was connected to a laptop running a proprietary software where we collected all the data. So these are the parameters we measured during the test: the brake temperature, vehicle speed, deceleration, gross vehicle weight, engine speed, GPS coordinates, brake application pressure, environmental conditions, and number of snaps. So here on this slide, you see the infrared sensors. We also had a handheld sensor to first calibrate the sensors and to validate readings from the sensors during the test. This is the controller box that was installed in the cab, and this collected data from the controller and power distribution boxes on the cab and the trailer. So this is the signal conditioning and power distribution box that was installed on the tractor. And this is the laptop, the Marcus X software. This is a proprietary software. It allowed us to see different parameters as the test was carried out. So on this slide, we could see the speed. We could also see the acceleration of the truck in real time during the test. And here we could also see the brake temperature for six of the brakes of the truck. For our loading, we use crates of water. So now to the test, the field tests, updating the GSRS. We conducted 3 main tests. These were the cool down, and hill descent tests. The cool down test was meant to measure the sum of the drag forces acting on the track. The cool down tests were meant to measure the cooling characteristics of the track. The hill descent tests were meant to define the heating characteristics of the track. And also on this slide, you see the GSRS model developed in 1980 by the FHWA. These are the model parameters we updated on this research. So before we proceed, I would like to talk about the brake temperature equation. This is an equation which relates brake system temperature to the speed of a truck. What this temperature model is meant to do is to define a certain speed such that the speed at the bottom of a downgrade is always less than or equals to a predefined limiting temperature. So this has been defined in equation 2. That is the basic concept of using the brake temperature equation, defining a certain speed such that the brake system temperature never exceeds a certain predefined limiting temperature. I also have to talk to you about the required braking force. This is an important concept in the GSRS model. So we consider a track of weight W, slope on a grade of slope theta. Then if the track is in motion, there are some drag forces acting on it. These are the aerodynamic drag, the powertrain drag, and the rolling resistance drag. There's also drag from engine braking and from resistance from the engine itself. These together are known as the non-brake forces. To keep the track at a controllable speed, the driver applies his brakes. This is known as the brake force. So if we sum forces in the downgrade direction, then we have W theta minus the braking force minus the non-braking forces. So we can derive an expression for the required braking force. So now on to our first field test. The first test we conducted was the cool sound test. As I mentioned previously, this was to determine the sum of the drag forces acting on the track. We used field tests, and we also had to supplement this test with simulation tests. We conducted the test according to the Society of Automotive Engineers J1263 and Environmental Protection Agency standards. So two different tests were conducted. First, we conducted the tests to measure the sum of the drag forces, and also we had to define the engine power absorption characteristics of the track. So with the coast down test, what is done is the track is driven to a predefined speed on a level ground. The track is put in neutral, and then it is allowed to coast to a stop from the predefined speed. The gear is in neutral to measure the sum of the drag forces, and to measure the engine power absorption characteristics, the gear is put, the engine brake is engaged along with the track gears for this second test. So the drag force is calculated according to Newton's law of motion. This equation is modified to account for the effective mass of the track, to also account for the slope of the test track. These are regressed against drag coefficients A, M, and D. So you here on the slide, you see an example of a velocity time trace plot of one of our coast down runs. Like I mentioned previously, we had to use simulation software to augment tests from the field. This was because in some cases, environmental conditions, the wind speed just didn't allow us to conduct our tests. So we used our simulation, and we developed a correlation between the field test and the simulation. So this was the overall drag force expressed in terms of vehicle speed. What we found was that when no compression brake was engaged, the horsepower, the braking horsepower was 63.3 from the engine. At full engine brake, the retarding horsepower was 502, measured at 1,800 RPM of engine speed. The second parameter we estimated was the diffusivity parameter, also referred to as K1. This was estimated using cool-down tests. Like I mentioned previously, the diffusivity parameter defines the cooling characteristics of the brakes, and this is also derived according to Newton's law of cooling. The Newton's law of cooling defines the relationship between a body's heat loss and its surroundings, and is expressed as the equation you see above. So from the equation, the equation implies that a plot of the natural log of temperature against time should result in a graph with the parameter minus K1 as the slope of this graph. So to conduct the cool down test, we drove the truck and heated its brakes by dragging to an average temperature of 500 degrees Fahrenheit. And we then drove the truck at various speeds, 0, 20, 30, and 45 miles an hour to allow the brakes to cool to ambient temperature. Then we plotted the natural log of heat loss against time for the brakes at different temperatures. So here on this slide, you see a K1 extraction at a speed of 0 miles an hour. And this is a variation of K1 with speed for the right brakes. So we got an overall expression for the diffusivity parameter in terms of speed for the whole brake system. The final parameter we had to estimate was the heating parameter, referred to as K2. This was extracted from hill descent test. We used the hill descent test to correlate brake temperature with the horsepower absorbed during a grade descent. We achieved this correlation by rearranging the terms of or the parameters of the brake temperature equation such that we have the thermodynamic variables on one side and the retarding force on the other side. The thermodynamic variables we refer to as T asterisk. And also, if you remember, I gave a definition for the required braking horsepower, the required braking force in one of the earlier slides. And so the required braking force times the speed of the truck should be the horsepower into the brake. So a plot of T asterisk, which is which represents the thermodynamic variables against horsepower into the brakes, should result in a graph with a slope of the heating parameter K2. So on this slide, I want to show you a hill descent test, one of hill descent tests. Here you see the truck descending a grade at a constant speed, and you have the Y dot vehicles providing traffic control. This downgrade leads to 10 sleep. Is on the western face of US 16. This leads to Warland, close to the little town 10 sleep. So we descended different hills at constant speeds by modulating the brake pressure. We conducted a test for different speeds, and we also used the retarder settings to simulate changes in the weight of the truck. This was done to speed up the test process. Here on this slide, you see a plot of T asterisks representing the thermodynamic variables against horsepower into the brakes at 10 miles an hour and at 21 miles an hour. So we did this at different speeds, and we derived an expression for the brake system in terms of K2. So that is the expression on the slide. So now we've updated all the parameters of the brake temperature model. So these are updated parameters. So from these updated parameters, we can now derive temperature plots by rearranging the brake temperature equation into the equation you see on your slide. So what we can do is for defined maximum descent speeds V, we could estimate what the downgrade length should be. It is also important to note that for our model, for our updated model, the limiting temperature is the sum of two temperatures. The temperature from a steady descent of the grade referred to as TF, and the temperature rise from an emergency stop. For study, we used a limiting temperature of 500 degrees Fahrenheit. This was because of the reasonableness of the speeds derived, and also to represent the general feed temperature for brick linings we had on our track. So on this slide, you see an example of a maximum safe descent speed plot for a track weight of 80,000 pounds. On the y-axis, we have the maximum descent speed, the Vmax. On the x-axis, we have the downgrade length in miles, and then we have these curves representing in percent. Let me go back here. So to derive a specific speed, let's say a speed of for a downgrade with certain features or characteristics. Let's say an 8% downgrade. This will be the 8% grid line at 6 miles. So 8% downgrade at 6 miles. It means an 80,000 pound truck should travel at about 40 miles an hour. That is how we use the maximum safe descent speed plots. We also conducted a validation test to check the robustness of our model, and this was done on the existing phase of US 16 from milepost 67.4 to 73.9. What this was, this downgrade was a multi-grade hill, meaning it had cooling and heating intervals. So you had places of descent, and you also had places where the track had to ascend. In the places where the track had to descend, that meant the brake system temperature increased. In places where the track had to ascend, brake system temperature cooled. So we measured the brake system temperature during our drive down the eastern phase of US 16, and then we predicted the brake system temperature. So on this slide, the field brake temperature is represented by the solid blue line, and the predicted brake temperature by the dashed line. Okay, so that brings me to the end of the test conducted to update the GSRS. Now I'll talk to you briefly about the safety effectiveness of downgrade warning signs. This was with respect to our second objective. So we conducted some analysis to evaluate safety effectiveness of downgrade warning signs in preventing track crashes. We conducted an overall analysis and an individual analysis of warning sign effectiveness. We used the propensity scores and cross-sectional analysis methods. Overall, what we found was that the probability of a downgrade track crash occurring on sections without downgrade warning signs was 15% higher in comparison to those sections with warning signs. So it was 15% higher on downgrade sections without warning signs compared to downgrade sections with warning signs. We found that track escape ramp signs, hill signs, directional and speed signs, chevron signs, tracker warning signs, and some other miscellaneous downgrade signs were effective in reducing crash frequency. So these are some of the warning signs we found to be effective. Track escape ramp, hill sign, directional and speed sign, chevron, tracker warning sign, and some miscellaneous downgrade signs. We also looked at the application of intelligent transportation system technologies in improving mountain pass safety. So some of these applications are already in use, others are potential application. So we looked at thermal imaging of brakes, dynamic track curve warning system, downhill track warning system. The curve warning system and the track warning system are already in place and they are already in use. We also looked at some vehicle-based systems, including automatic emergency braking systems, intelligent speed adaptation on board train systems. And then we also looked at potential applications of connected vehicle technologies in improving mountain pass safety. These include reduced speed zone warning, spot weather impact warning, size vehicle warning. We should note that a lot of these technologies are still several years away from being developed or being implemented. Vehicle-based systems included in-vehicle signage, control loss warning, and forward collision warning. Analysis, our findings, and recommendations from this research have been presented in two reports, which have been submitted to Wyoming Department of Transportation in two volumes, volume 1 and volume 2. Volume 1 of this report is currently online and it can be downloaded, but volume 2 has not been uploaded yet. Anyone interested in any volume of this report can contact the Y. Research Office to purchase a copy. So now to the formulation of weight-specific speed signs. I should also mention that a user's manual to the updated GSRS is written and is currently in possession of Y. It has been submitted to Y. So I'll take you through an example of the formulation of weight-specific speed signs at this point. So there are some activities the engineer has to first undertake to derive maximum descent speeds and to formulate these weight-specific speed signs. First, the engineer has to identify potential sites in need of weight-specific speed signing. This involves an analysis of track crash data, traffic data, geometric data, police records, to identify hazardous locations that may benefit from installation of weight-specific speed signs. After these candidate sites have been identified, the engineer has to perform a field inspection of these sites and verify the percent, the downgrade percent, the length of the downgrade, track braking length, traffic control types at these sites. Then the third step is to determine the grade severity using our updated model. So maximum safe descent speeds for different track weight categories are estimated using the grade percent and track braking length. Then the fourth step is to determine the weight-specific speed signing needs. This is done by determining the appropriate weight intervals and recommended speeds that have to be displayed on the weight-specific speed sign. The final step is to install the access signs. So these are the steps that have to be taken in actually formulating the weight-specific speed signs. There's a lot written here, but I'll simplify it. So important things the engineer has to determine is the track braking, the grade percent, the track braking length L, and the maximum load limit, as well as the maximum speed limit on the downgrade. So I'll say this again. The engineer has to determine the grade incline or the grade percent, the track braking length, the maximum load limit, and the maximum speed limit on the downgrade. Also, the engineer has to determine the lowest weight at which the truck can travel at the speed limit of the roadway under consideration. So the engineer has to use temperature plots, the maximum descent speed plots, to determine the lowest weight at which the truck can travel at the maximum speed limit. This will become clearer as we go through the example. Then the next step is to compute the number of weight intervals between the maximum weight limit and this lower weight limit, which we refer to as WL. That is the weight at which the truck can travel at the speed limit. So the number of weight categories is determined as the difference between the maximum weight for the facility and that lower weight we will determine divided by 5,000. If the number of weight categories is less than or equals to 5, then the weight categories to be put on the WSS sign will be in 5,000 pound intervals. Now, if the number of weight categories is greater than 5, then the number of weight categories to be put on the WSS sign should be 10,000 pound interval. We are restricting the number of weight categories to be placed on the weight specific speed sign to make it easy for drivers to read if they are traveling at the operating speed at the facility. So you want the drivers to be able to just take a quick look at the weight specific speed sign, determine their weight category and determine the speed that corresponds to their weight category. Finally, the speed associated with each weight interval should be the speed for each weight category should be the highest speed for that category. So if you have a lower weight and a higher weight for a specific weight category, the speed to be displayed on the WSS sign should be that speed corresponding to the heavier weight category. Again, this will become clear if we go through an example. So let's go through our case study. Supposing we have a downgrade incline of 7%. The engineer has determined that the braking length should be 6.5 miles. The maximum weight for this facility is 80,000 pounds, and the speed limit is 55 miles an hour. Our first step is to determine the number of intervals that should be placed on the weight specific speed sign. We have to remember that to get the number of weight intervals, we have to determine that weight at which the truck can travel at the speed limit. So to do this, we go back to maximum speed descent plot. Let's remember, our downgrade incline is 7%, our braking length is 6.5 miles. So going back, we remember that our maximum weight is 80,000 pounds. So we go to our plot and see. So again, you have the maximum descent speed on the y-axis, and then you have the downgrade length or the track braking length on the x-axis. Then you have the speed plots for the different grades, which are represented by the curves on this graph. So remembering that our downgrade incline is 7%, we have length of 6.5 miles. So first we trace 6.5 miles on the x-axis. This is 6.2, 6.4, this is 6.5. Okay. Then we look at this 6.5 mile grade curve. So 6.2, 6.4, 6.2, 6.4, 6.5. Trace it to the 6.5 mile curve. They're about 6.5 miles, 7%. Okay, so 7%, the curve is rather 7%, and this is 6.5, 6.2, 6.4, 6.5. So this is the 7% grade. Trace it from here So this is about 18 miles an hour. We do the same for a weight of 75,000. So we are decreasing in 5,000 pounds intervals. So another, so we have a 7% grade, we have 6.2, 6.4. Then we trace a line from the 6.5 mile line up to the 7% grade, and then we trace it to the y-axis. It should be about 22 miles an hour. Do the same for 70,000, 65,000, and then 60,000. Let's check for 60,000. This is the 7-mile grade. This is a length of 6.5 miles, represented by this line. So tracing it up, you can see that these two do not intersect. The curve does not intersect the 6.5 mile line on this graph. They intersect somewhere outside the graph. Importantly, what this means is that a truck of 60,000 pounds can travel at the speed limit of 55 miles an hour for these downgrade specifications. So our lower weight limit, WL, at which the truck can travel at the speed limit is 60,000 pounds. So if you remember, the number of weight categories is calculated as the difference between the maximum weight and the weight limit on that facility and the lower weight limit at which the truck can travel at the speed limit divided by 5,000 pounds. So we have 4 categories. This implies that the number of weight categories we place on the WSS sign should be 4. Also remember that if n is 5 or less, the column of weight should be in 5,000 pound intervals. So for our scenario, the column of weight will begin with the lower weight limit, which is 60,000 pounds, and increase in 5,000 pound increments to 80,000 pounds. So these are the maximum truck weights and corresponding speeds we derive from a maximum descent speed plot. So you have 80,000, 18 miles an hour, 75,000, 22, and so on and so forth. 60,000, 55 miles an hour. So what we now do is we have to place them in weight categories. Remember that because n is less than 5, the categories can be in 5,000 pound increments. So you have 70, 61 to 65,000, 66 to 70,000, 71 to 75,000, and 76 to 80,000. It is important to note that we do not repeat weight categories. So you have 65,000 pounds as the heavier weight category on this weight interval, but in the next weight interval we don't have 65,000, we have 66,000. This is to avoid confusion and simplify the task of reading the weight specific speed signs. So we put them in these categories. Now, importantly, for each weight category, the speed to be displayed on the WSS sign is the speed corresponding to the heavier weight for each weight category. So for 80,000 pounds, go back to our maximum truck weights we found. So 80,000. The interval is 76 to 80,000. So we go to 80,000, the weight corresponding to 80,000, because that is the heavier weight category between these two. So 80,000. It is 18 miles an hour. But because we normally do not display speeds, because we normally display speeds as round figures, we round this 18 miles an hour to 20 miles an hour. We go to 75,000. The corresponding weight for this weight interval for 75,000 is 25 miles. It's 22 miles an hour, but we round it up to 25 miles an hour. Between 66,000 to 70,000. So 70,000 is the heavier weight category for this weight interval. So we go to 70,000, it is 29 miles an hour. We round it up to 30 miles an hour, which is what we'll display on the sign. Between this weight category, you have 61 to 65,000 pounds. 65,000 pounds is the heavier of these two weights. So we go back to weights, and then 65,000 pounds, it is 42 miles an hour. We can display a speed of 40 miles an hour. So these are the advisory maximum descent speeds that you display on the specific speed sign, and which should be installed by the side of the road for our downgrade, which was 7%, which had an incline of 7% and a length of 6.5 miles. I'm sure you have some questions, and maybe Chris will let us know as we move on. Now to the recommendations of the study. We found that the GSRS model, if implemented, will enhance track safety on Wyoming mountain passes. However, the maximum safe speeds displayed on the WSS sign cannot be currently enforced and are to be treated only as advisory speeds. This is because an enforcement officer can in no way tell the weight of the truck. Also, drivers should be educated on the use of the GSRS and weight-specific speed signs. The education should focus on improving mountain driving for inexperienced drivers and for those who are unfamiliar with Wyoming's mountain passes. The trucking industry should be encouraged to adopt and install disc brakes. This has been widely done in Europe, but the penetration of disc brakes in the US market has not been as fast as expected. Disc brakes are known to be resistant to brake fade, and their adoption will reduce the incidence of truck runaway crashes. Also, the GSRS, the weight-specific speed signs, will be meaningless if brake systems are not checked regularly and maintained. One thing which is prevalent on a lot of truck fleets is brake imbalance. That means you have some brakes doing all the work and some brakes not doing any work at all. When you have such brakes on a truck, which is very unbalanced, then the GSRS is not directly applicable, and this should be paid attention to. The GSRS was developed primarily for trucks that have not been equipped with retarders. However, a substantial proportion of trucks on US highways have been equipped with retarders. These should be set to their maximum setting on downgrades, and then the truck should descend the downgrade at the highest speed displayed on the WSS sign. So for this study, test truck was fitted with disc brakes on the steer axle. However, the current penetration of disc brakes is about 20%. At the time this study was done, it was about 20%, and this is still growing. The GSRS will become more applicable to the US trucks as the penetration rate increases. And so we recommend that before-after studies should be conducted after the implementation of the GSRS and WSS signs to assess their safety effectiveness. Also, feedback from drivers should be encouraged, as this will improve the implementation of the GSRS. So for future studies, more tests have to be conducted to validate the GSRS model. especially for higher truck loads and axles. Also, it will be important to validate the GSRS model for those trucks which are fitted with only drum brakes for all the axles. Also, to enable easy implementation of the GSRS, a software should be developed. This will be very beneficial and make the implementation process very easy. Also for multi-grid hills, those hills with cooling sections and heating sections, those with upgrades, level sections, downgrades, all together in one downgrade. The use of the software will make calculations easy because the calculations as we've done it do not really apply to these multi-grid hills. It only applies to single grids. Also, the presence of curves on downgrades should be incorporated into the procedure for estimating maximum descent speeds. This can implemented in the software easily. Then, like I said before, before-after studies should be conducted after the GSRS has been implemented. So this is the end of my presentation. I would like to acknowledge the efforts of Admiral Transportation Company up in Warland, donated their truck to us for us to instrument and conduct these tests. Efforts of Traffic Safety Coalition is also appreciated, and to our partners who funded this project, the Wyoming Department of Transportation and Mountain Place Consortium. They deserve a lot of appreciation. Thank you, and I'll take any questions if you have them.
Okay, awesome. Thank you, Milhan, for that sharing that information. It was very, very valuable, very good information. A lot of work and a lot of time spent on that, so thank you for that. Visit our website at translearning.org for upcoming learning opportunities and to access our learning management system. We do have one question. Can you explain what is CAN bus?
Hello.
Yep.
Okay. So the CAN bus is a sort of controller area network system. This enabled us to it's some sort of protocol which enables us to like connect to the truck engine, the truck computer system, and then get our parameters, the parameters that we required. So that is the CAN bus.
Excellent, thank you. Okay, not seeing any additional questions. It is 11 o'clock and we were scheduled for 1 hour. Thank you again for attending. I appreciate your time and attention today. Dr. Moomin, thank you very much for sharing this information, and everybody have a great and safe day.
Thank you.